Welcome. Our project is a smart elderly care monitoring platform. Think about a caregiver who is responsible for elderly patients in different rooms. Caregiver cannot be in all rooms at the same time. What if someone has a fever at night? What if heart rate becomes dangerous and no one notices? This is the problem we wanted to solve. Our solution is a system that monitors every room automatically 24 hours a day. It collects sensor data, stores it, detects dangerous situations, and immediately notifies the caregiver. This is our system architecture. At the bottom, we have the catalog. It is the core of the system. It stores the list of all devices and caregivers. In the middle, we have the message broker. This is MQTT. It carries all data between components. On the right, we have the device controller, the Raspberry Pi in each room, which collects sensor data and sends it to the broker. On the top left, InfluxDB stores all the data through the adapter. In the processing group, the event trigger checks for dangerous values and the report generator creates summarizes. On the bottom left, the web dashboard and Telegram bot show the data to caregivers. Each part is an independent microservice. Let us explain all of these microservices.
This is the catalog service, the central registry for our IoT elderly care platform. Every other microservice in the system talks to this one at the startup to get configuration, find each other's URLs, and understand which caregivers are responsible for which rooms. It is a REST API framework built with CherryPy and it runs on port 8000. First, we have the data model. We have three classes: device, service, and caregivers. The most important thing to notice here is that device class can carry a list of caregiver IDs, which means that each device could be monitored by one or more caregivers. Then we have JSON store class. Persistence is handled by this class. It keeps everything in memory and writes to a JSON file on every change. This line here ensures that admin caregiver always exists. And this here ensures that all existing devices are assigned to admin. Let's pass to the catalog app. Here we can show that four method signatures are existing: get, post, put, and delete. The HTTP layer uses CherryPy's method dispatcher. Each HTTP verb maps directly to a Python method. These methods, get, post, put, and delete, all live here. The URL structure is clean REST. Let's see an example. For caregivers, as an example, we have /caregivers or /caregivers/ID or /caregivers/ID/devices. So no routing framework is required here because CherryPy handles it automatically. To sum up, the catalog service is a lightweight but critical piece of our architecture. It is the single source of truth that makes the entire microservice ecosystem coherent.
Each room in our system has one Raspberry Pi. In a real hospital or a care home, this would be a physical device on the wall. In our project, we simulate it with a Python program. The important design decision is this main.py. Every room runs the same code, the same main.py file. The only difference is a small configuration file called sitting.json. This file contains the room ID, for example, room 1, room 2, room 3, or room 4. This is how we simulate 4 independent devices. Raspberry Pi reads 7 sensors: temperature, CO2, humidity, heart rate, body temperature, and blood pressure. For the patient's vitals, let's run Raspberry 1. When Raspberry 1 runs at terminal, it first registers itself in the catalog. Uh, After subscribe to uh, our telemetry. This is our catalog.json, and you can see room 1. That is connected to MQTT broker and begins publishing data every 10 seconds. One message for environment. Let's show you the telemetry. Room 1, as you can see, one for environment and one for vitals. Here you can see the terminal. Room 1 is running, register successfully.
In this part, I want to explain about InfluxDB, which is the database used in our project to store sensor telemetry. Its role is really important because our system continuously receives measurements from different rooms and different sensor types. So we need a database optimized for time-based data. Here is the dashboard of the InfluxDB. Inside it, we have created a bucket with the name of the elderly care role for our project. In our case, the stored data is divided mainly into measurement, environment, and vital. Here we can see that the database contains information from multiple devices, for example, room 1 to room 4. We also store multiple sensor types such as temperature, CO2, humidity, heart rate, blood pressure, and body temperature. So InfluxDB is not storing only one value, but a complete stream of sensor information from the project. Each data point is stored together with important metadata such as timestamp, the device, the sensor, the unit, and the value. This is useful because we do not only want to know the latest reading, but also the history of the readings over the time. For example, we can analyze trends, build dashboards, and retrieve past measurements for reports. Another service in our project is Influx Adapter, which is the component in our project as a bridge between MQTT telemetry, inflexible storage, and the other application services like report generator and the dashboard, which is Node-RED in our project. First, the adapter reads its basic configuration from setting.json. Here we define the catalog URL, the service ID, the service URL, and the service description. This allows the adapter to register itself in the platform and to be discovered by the other components. The adapter first loads this configuration file, then it reads the InfluxDB setting from the Docker environment variables, such as the URL, the token, organization, and bucket. After that, it contacts the catalog to dynamically retrieve the MQTT broker address ports, and topic prefix. This makes the service more modular in our project. Once the configuration is ready, the adapter creates the MQTT client and subscribes to all telemetry topics under the selected prefix. In this way, it can receive sensor data from all rooms and all devices through the broker. The core logic is inside the notify method, which is called every time a new MQTT message arrives. The adapter parses the JSON payload, extracts the device ID, timestamp, sensor name and value and unit, and then decides the measurement type, for example, environment or vital, and after that it creates an InfluxDB point for each sensor reading. The adapter also exposes REST import using cherry pie. For example, get data returns the latest value of a sensor, and here get history returns historical record for a device, and get series return a time series for one specific sensor. These APIs allows other services to access the stored data in a simple way. So, in summary, the Influx adapter connects MQTT telemetry, Influx DB storage, and data access for services like Node.net and report generator.
The event trigger microservice monitors incoming sensor data and generates alerts whenever environmental or vital parameters exceed safe thresholds. At startup, the service registers itself to the catalog and retrieves configuration data. This configuration includes the MQTT setting and the threshold values for sensors. As we can see here, thresholds are dynamically loaded from the catalog, meaning they are not hard-coded and can be updated centrally. The service subscribes to telemetry topics via MQTT. When a message arrives, it is forwarded to the event trigger service through a notifier class. The incoming MQTT message contains sensor data in a SNML standard. This data is converted into a dictionary, so each sensor value, such as temperature, CO2, etc., can be easily accessed and processed. Each value is then compared against the configured threshold. If any of these parameters goes outside the safe range, a danger condition is triggered. Now I show you the system in action. I am subscribed to the alert topics to monitor the messages generated by the service. When a sensor value exceeds the threshold, the service immediately publishes an alert. Here we can see the alerts containing room, the abnormal values, and the status, which is set to danger. In summary, this microservice enables real-time monitoring by transforming raw sensor data into meaningful alerts, ensuring timely detection of unsafe conditions in the IoT environment.
This is the report generator, the data science layer for our IoT LLK platform. This service looks back over historical data and computes meaningful statistics, time-weighted averages, threshold violation hours, clinical percentiles, and sensor correlations. The service is split into 4 clean layers, each with one responsibility. Catalog client handles a startup. It fetches configuration and discovers the InfluxDB adapter URL through service discovery. Adapter client fetches historical sensor data and converts it into a pandas data frame. Statistics engine is pure computation, no I/O, no state, just math. and report builder orchestrates all three to produce the final report. The most important part is the statistics engine. Here we have compute TWA, the time weighted average. This is more accurate than a simple mean because it weights each reading by how long it persisted. So if CO2 spiked for 2 hours, that contributes more than a brief 5-minute fluctuation would. Then we have compute time above and compute time below. These answer a clinical question. Not just whether a value crossed a threshold, but for how many hours. That is a difference between a transient spike and a persistent problem that needs attention. The rest layer is a thin wrapper. It just delegates to the report builder. We have 3 endpoints here. /env returns the environmental report, CO2, temperature, and humidity with the time weighted average and hours above or below threshold. /vital returns the patient vitals report, heart rate, body temperature, and blood pressure, adding clinical percentiles like P5 and P95 and a heart rate variability measure. /summary is designed for dashboards. It returns a single room status field, either OK or warning, with a plain English description of what is out of range. In summary, the report generator turns raw time series data into insights that a doctor or facility manager can actually act on. 3 endpoints, 4 clean layers, and a statistics engine built entirely with pandas and NumPy. This is the Telegram bot, the human interface for our IoT elderly care platform. Once it starts, connects to the broker, subscribes to alert and telemetry topics, and begins polling Telegram for user input. The first thing a caregiver sees is a login prompt. The bot asks for a username, looks it up in the catalog service, and if found, loads the caregiver's assigned rooms. After login, the dashboard shows the caregiver's name, their assigned rooms, and their current alert status. From this point on, the caregiver automatically receives alert messages whenever a threshold breached in any of the rooms. Pressing My Rooms gives a quick list of all rooms this caregiver is responsible for. Pressing Get Instant Reading shows an inline keyboard with 1 button per room. The caregiver taps a room and the bot publishes an MQTT request to that device, including environment, sensors, and patient vitals. The caregiver can also pause monitoring. The button toggles between stop and start monitoring, and the dashboard updates to reflect their current status. While paused, automatic alerts are suppressed for that user only. Other caregivers assigned to the same room still receive them. Finally, logout clears the session completely and returns to the login prompt. The entire bot is in one class, Telegram bot. The constructor loads config settings. It then initiates the 4-state data structures you just saw in action. Two MQTT callbacks are wired up here. On connect, subscribes to alert and telemetry topics once the connection is established. On message is the single entry point for all incoming MQTT traffic. It checks the topic and routes to either handle alert or handle telemetry response. Inside handle alert, these lines do the targeted delivery you saw in the UI. It filters sessions to find caregivers assigned to that room by skipping anyone who passed monitoring. For instant readings, inside handle callback query, a UUID is generated, stored in pending with the caregiver's chat ID and published to the device as a correlation ID. When the response arrives, the bot pops that ID from pending and knows exactly who to reply to. To sum up, we have real-time push alerts, on-demand live readings, per caregiver monitoring control, all with no custom front-end.
This component of our system is the dashboard implemented using Node-RED. It provides real-time visualization of sensor data stored in InfluxDB and reports generated by the report generator microservice, enabling both monitoring and historical analysis. Node-RED uses a flow-based approach where nodes are connected to process data. The dashboard supports two types of users, caregivers and administrators. When a caregiver logs in, he or she can access multiple functionalities. In the live monitoring page, the user can select a room based on his or her accessibility to devices. User can choose a room through a drop-down menu and view the latest sensor values, which are retrieved from the InfluxDB. In the Data Insight page, we can see aggregated statistics such as average, minimum, and maximum value. These are generated by the report generator microservice based on the selected time period. The historical trend page displays sensor data as a line chart, allowing the user to analyze trends over time by selecting the room, sensor, and the time range. Finally, user can log out from the system. In addition to these features, administrator has extended control over the system. Admin can access to all devices. Moreover, admin can manage caregivers by adding or removing user retrieved from the catalog. Admin can also view and delete registered devices which correspond to rooms in this system. Finally, admin can assign devices to caregivers, defining which rooms each caregiver can monitor. It is important to mention that the admin will have access to all devices as soon as a device registers itself in the catalog during initialization. In summary, the dashboard provides a centralized and role-based interface for monitoring, analyzing, and managing the IoT system.